Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today, we're going to introduce vector spaces. There are different ways of defining the concept of a vector space. Here, we will only deal with what are called real vector spaces. A vector space will be a set together with a field and two operations that satisfy a number of properties. The field, for us, will be the field of real numbers, though that field can be any field, like the complex numbers or the set of integers modulo n, any number of different possible fields that can be used. We will look only at real vector spaces in this course. In general, a vector space is a set V together with a field, which I'll denote by Blackboard bold F. We will use only the real numbers as our field. And two operations. The first one is going to be denoted by circle plus. We're being a little cagey here. This notion of vector space is be a generalization of Rn. And circle plus is going to correspond to our notion of vector addition in Rn. The way it works is it takes as input an ordered pair of things that are in the vector space and outputs something in the vector space. I want you to note something about this definition. This is called a binary operation because it takes in two things and outputs one. And it outputs in the vector space. So built within this notation itself is the notion of closure under addition. That's already built in to this notion of binary operation. That's the first of the two binary operations. It's called vector addition. The second operation is called scalar multiplication, and we're going to denote it by circle times. It's going to take something in the field and something in the vector space and output something in the vector space. Note again, the closure law for scalar multiplication is built in to the definition of this operation. These operations must satisfy the following properties. I enumerate 10 vector space properties. A lot of people list 8, and some list fewer than that. I'll show you how in a minute. The first property is already built in. It's the closure law. Of addition. It goes like this. If U and V are elements of the vector space, then when I add U plus V, circle plus, I'll get something in the vector space. This is already built into our notion of binary operation. The associative law is not. It goes like this. If U, V, and W are elements of the vector space, then U plus V plus W will give you the same result as U plus V plus W. And then there's the Commutative Law of Addition. And it goes like this. If U and V are in the vector space, then U plus V, circle plus, gives you the same result as V plus U. We're abstracting all of these properties, and we'll come up with a large class of different vector spaces. The theory that we develop will apply to any one of them that we wish to study. And property 4 is the existence of a zero vector. There exists a vector which we'll denote by 0 with a little half arrow over the top that lies within the vector space, so satisfying for any other vector in B. When you add U plus the 0 vector, or the 0 vector plus U, it leaves it alone. That's how 0 should behave. For any vector V lying in the vector space, there exists minus V satisfying V plus minus V is minus V circle plus V equals a 0 vector. Those first 5 are the purely additive properties. Property 6 is the closure law of scalar multiplication, which technically is already built in. It goes like this. If A is an element of our field, and V is an element of the vector space, then when you take A times V, you get something in the vector space. These are not very complex properties, but you'll see some interesting examples. There is an associative law for scalar multiplication. If A and B are in the field, and V is in the vector space, then A times the quantity B times V gives you the same thing as A times B, and then times V. Notice this times and this times are not the same times. This is the times that works in the field. For real numbers, that's just like saying 2 times 3. But the other times is where you take a scalar, something in the field, and multiply it by a vector. Those are not necessarily the same thing. Property 8 is the property of 1. Every field has a number that is called 1. And it goes like this. If you take some vector in the vector space, then when you multiply 1 times that vector, you'd better get that vector. We want this to be true. And then we have 2 distributive laws. If A and B are in the field, and V is in the vector space, then A plus B times V, and this is not the circle plus, this is the regular plus from the field, is equal to A times V circle plus. B times V. Have to be careful about the way in which we express these operations. And then distributive law number 2. We want A to be in the field and U and V in the vector space. Then A circle times U circle plus V is A circle times U circle plus A circle times V. The obvious example is Rn, under the usual notion of vector addition and scalar multiplication that we've already seen. We had a theorem showing that Rn, together with those operations, satisfies the 10 properties of a vector space. Now, I mentioned that it could be 8 properties. A lot of times, instructors will leave off the 2 closure laws thinking that they're obvious, they're built in. They're not wrong. I just like to make it very explicit. I want you to know that those 2 are required. Also, some professors will introduce a concept called a group. It's a set G together with a binary operation plus, which maps G cross G into G. It takes 2 group elements, and when you add them, you get a group element. Sounds like a closure law. Such that, 1, it has to be associative, so that A plus quantity B plus C is equal to A plus B plus C. There must exist an additive identity Now, the tradition for groups is to not denote the 0 by a vector 0, but rather by the lowercase letter e. It behaves like 0. If you add it to another group element, you get that other group element. Each element must have an additive inverse. For each element of the group, there exists some minus g, and this isn't the usual notation, but we'll go with it, such that when you add g to minus g, you get the same thing as when you add minus g to g, and that is the identity. Note what is missing from this definition of a group. We did not assume the commutative law. Many groups are not commutative. Now, if we want the group to satisfy the commutative law of addition, we have to assume that. And then the group is called an abelian group or a commutative group. If a group satisfies the commutative law or the commutative property, it is called an abelian group after the famous mathematician Abel, or commutative group. Note that a vector space is an abelian group under the group operation plus. Sometimes mathematicians will eliminate the closure laws and have 8 properties for a vector space. Sometimes, if you group the closure law, the associative law, the existence of an identity, the existence of additive inverses, and the commutative property, the first 5 properties, those can be grouped into one property, the assumption that we have an abelian group under the operation plus. That leaves the other 5 properties. If we group the first 5 properties into one, that the vector space forms an abelian group under the vector space operation plus, then we only have the remaining properties. Listing the closure law of scalar multiplication as part of just the definition of scalar multiplication, we can limit our number of properties to 5. We've already seen that Rn forms a vector space for each n. That gives you an infinite list of examples, but so does the set of m by n matrices. This will form a vector space as well under addition of matrices and scalar multiplication of matrices. I want to give you an interesting example. Let V be the set R plus. Only positive numbers are here. And define our notion of addition so that U plus V, positive real number plus positive real number, is, by definition, because I said so, U times V. And suppose that U circle times V is U to the power of V. I ask, do we have here a vector space? We need to go through the properties. Is this a vector space? If you add two positive real numbers by multiplying them, you still have a positive real number. So it does satisfy the closure rule. What is more, this notion of addition is associative because multiplication of real numbers is associative. It's commutative because multiplication is commutative. What is the notion of zero under this operation? Zero is the number in the positive real numbers, so that if you take that number and circle plus it, that means multiply it times another number, you get that other number. So whatever that zero is, when we circle plus it to some other vector, in other words, that zero times V will be equal to V, it becomes clear that since our addition operation is multiplication, that zero is the number 1. Under these operations, if I have 1 circle plus any other number, that's going to be 1 times that number, and gives me the other number. So 0, the 0 vector, is 1 under this operation. You might ask, what is the additive inverse of 2 under the circle plus operation? Normally, it's the thing that when you add to 2, you get 1. But the circle plus operation is times. So the additive inverse must in fact be 1/2, because 1/2 times 2 is 1. So in our particular operation, circle plus, the additive inverse is the usual multiplicative inverse, because addition is multiplication. Note that 1 circle times 2, according to this definition, is 1 to the power 2, which is 1. And that's not 2. So this fails to satisfy the property of 1. Eliminating this definition of circle times and replacing it with the definition u times v is v to the power u. What happens then? Now, 1 times some number is going to be that number to the power 1, which is just that number. So it does satisfy the property of 1 now. Does it satisfy the other properties of multiplication? You can see that if we have a times the quantity b times c, we have a times c to the power of b, according to our definition. And that's going to be c to the b to the power of a, which we can rewrite as c to the a times b through the property of exponents. But that is a times b circle times c. So we do in fact satisfy this associative property. It certainly satisfies the closure property, because if you take a positive real number and raise it to a positive value, you will get a positive real number. So we have the closure property, the associative property, and the property of 1. That leaves only the distributive properties. Let's look at distributive property number 1. Suppose we have a plus b circle times the vector u. According to this definition, what you have is u to the power of a plus b. That, according to the usual rules of arithmetic, is u to the power of a times u to the power of b. But times is our circle plus. So that's u to the power of a circle plus u to the power of b. And those are a circle times u circle plus b circle times u. We get the distributive law. Let's try the one more property. Suppose we have a circle times u plus v, circle plus. This is, according to our rules, a circle times u times v, according to the usual notion of multiplication of positive real numbers. And this is u times v to the power of a. Again, according to the usual rules of arithmetic, that's u to the a times v to the a. And that gives you u to the a circle plus v to the a. And that is a times circle times u circle plus a circle times v. So we get both of the distributive laws. With this notion of circle times scalar multiplication, we now have a vector space. Suppose, in our next example, that the vector space is the set of real numbers, but we're going to make a non-standard notion of addition. We're going to suppose that u plus v is 3u plus 3v. How does this work? Is it a vector space? We're going to assume that the multiplication a circle times u is the usual multiplication. What could go wrong? Well, is there a 0? 0, circle plus v, is supposed to be, according to this definition, 3 times whatever that 0 is, plus 3 times v, but according to the definition of a 0, that has to be equal to v. What is this 0 that's supposed to work for all vectors v? You can see that you'd have 3 times our, whatever this 0 is, we don't know what it is minus 2v, and you can divide the 3 off. Would 0 always be negative 2/3 v? What if v is 0? Would 0 equal 0? What if v is 1? Would 0 be negative 2/3? Do you get a different 0 depending upon the number that you're working with? Doesn't that kind of defy the whole notion of 0? So it looks like the 0 does not exist. There is nothing that behaves like a 0 for all real numbers. This means that we do not have a vector space. What if we define the vector space to be the set of positive numbers, and we define u plus v to be v to the power of u, and u times v to be u times v, the usual notion of times. Note that 2 circle plus 3 is 3 squared, which is 9. But 3 plus 2 is 2 cubed, which is 8. We deduce that this is not commutative, and hence it is not a vector space. In our next example, we're going to let our vector space be R2, but we're going to monkey with the notions of addition and scalar multiplication. We're going to make the following definition. When you circle plus vector AB with vector xy, you get, by definition, definitions you must accept, theorems we prove. A plus x plus 1, b plus 1 plus 1. Also, if I take a constant a and circle times it, times the vector xy, I'm going to define that notion of scalar multiplication to be ax plus a minus 1, ay plus a minus 1. Is this a vector space? First, note that this definition of vector addition and this definition of scalar multiplication are both closed. They satisfy the closure laws. That gives us 2 of the properties right away. We have to check the remaining 8 properties. Let's begin with the Associative Law. Let's take AB, circle plus, LM, circle plus, XY, and we'll compare that to AB, circle plus, LM, circle plus, XY. In this first grouping, we get AB plus L plus X1, M plus Y plus 1, which is equal to A plus L plus X plus 1 plus another 1. and then b plus m plus y plus 1, and then plus another 1. Every time we add, circle add, we get another plus 1. Below, we'll have a plus l plus 1, b plus m plus 1 plus xy. And that gives us a plus l plus x plus 1 plus 1, b plus m plus y plus 1 plus 1. Since these are equal, we deduce that this operation, circle plus, is associative. Is it commutative? Let's take AB and circle plus xy. According to our definition of addition, this is a plus x plus 1, b plus y plus 1. The usual notion of addition is inside of these coordinates. We can use the regular commutative law to write this as x plus a plus 1, y plus b plus 1. And then, by our definition of circle plus, that's xy, circle plus ab. This notion of addition is commutative. Does there exist a zero? We don't know what zero is a priori. Let's just give it some coordinates, a and b. When you add 0 to something else, x, y, you're supposed to get the something else. In this case, we'll get a plus x plus 1, b plus y plus 1, and that's supposed to be xy. When you add 0 to something, you're supposed to just leave that other something alone. That tells us then a has to be minus 1 and b has to be minus 1. So the 0 vector is the vector minus 1, minus 1. Do we get additive inverses? Remember, an additive inverse satisfies negative of u plus u, whatever this is, adds up to the 0, whatever that is. So for us, it looks like if u has coordinates x, y, let's suppose that minus u has coordinates a, b. Then minus u circle plus u is a plus x plus 1, b plus y plus 1. That's supposed to be the 0 vector, which in our case is minus 1, minus 1. We can see then that a must in fact be minus x minus 2, and b must be minus y minus 2. So the negative of u will be negative x minus 2, negative y minus 2. Now, just as a reminder, we've defined a circle times xy to be, by definition, ax plus a minus 1, ay plus a minus 1. Does this satisfy the associative law? Let's take a circle times b circle times the vector xy. According to our definition, this is a circle times bx plus b minus 1, by plus b minus 1. And now when we perform a circle times that, we get a times bx plus b minus 1 plus a minus 1, and a times by plus b minus 1 plus a minus 1. And so what is that? We'll get ab times x plus ab, and then minus a plus a, those will cancel, and then minus 1. We'll get aby plus ab plus a minus 1. But you can see that is a times b, circle times xy. That means it is associative. Do we satisfy the property of 1? One circle times any vector is supposed to leave that vector alone. We get 1 times x plus 1 minus 1, and 1 times y plus 1 minus 1. And that is xy. It satisfies the property of 1. That leaves 2 more properties, the 2 distributive properties. If this is going to fail, it has to fail there. Let's look at a, circle times the quantity xy plus, circle plus, lm. That's going to be a, circle times x plus l minus plus 1, y plus m plus 1. And that gives us a times x plus l plus 1 plus a minus 1, and a times y plus m plus 1 plus a minus 1. Now we have to look at what happens on the other side of the distributive law. Let me make a note. We have a times x plus l plus 1 plus a minus 1, and a times y plus m plus 1 plus a minus 1. Let's look at a times xy, circle plus, a times lm. This will give us ax plus a minus 1, ay plus a minus 1, circle plus al plus a minus 1, am plus a minus 1. And now for our circle plus, we'll have ax plus a minus 1 plus al plus a minus 1 plus 1, and ay plus a minus 1 plus am plus a minus 1 plus 1. Let's see what we get. We'll have ax plus al plus this a gives us a plus 1. We still have this plus a. We have a negative 1 and a 1, and that gives us minus 1. That's the same as here. Similarly, a times y plus m plus 1 plus a minus 1 results in the second coordinate. That verifies the first distributive law. The one remaining distributive law. Let's look at a plus b times xy. According to our definition of circle times, this is going to be a plus b times x plus a plus b minus 1. And we also have a plus b times y plus a plus b minus 1. Now on the other side, we have A times xy, circle plus B times xy. Let's see what we get. We'll get ax plus a minus 1, ay plus a minus 1, circle plus bx plus b minus 1, by plus b minus 1, and then, according to our definition of circle plus, we'll have ax plus a minus 1 plus bx plus b minus 1 minus 1 plus 1, and ay plus a minus 1 plus by plus b minus 1 plus 1. How does that all work out? We'll have a plus b times x plus a plus b. We have a 1 and a minus 1 that cancel, and we end up with minus 1. Similarly, we'll have a plus b times y plus a plus b minus 1. Since we get equality between these two, the final distributive law holds. We deduce it is a vector space. We're forcing you to go through these properties because we want you to learn abstractly what a vector space is. It requires a bit of thinking to go through each of these properties to verify whether or not some given construct represents a vector space. Let's do another example. In the next example, let's let our set V be the set of real numbers, and we'll define U circle plus V to be U times V, and U circle times V to be V to the power of U. Now, you might think that we've done this one before, but in the example that we did earlier, we assumed that the set was the set of positive real numbers. I'm going to ask, is this a vector space? Try this one on for size. Let's take 1/2 circle times -1. According to our definition, this is -1 to the power of 1/2. And you know that that's the imaginary unit I, which is not in this vector space. This is not closed under multiplication. That means it is not a vector space. In our next example, we're going to let f AB be the set of all real-valued functions with domain equal to AB. Is this a vector space? In fact, most of the really interesting examples of vector spaces are function spaces like this. If you take two real-valued functions and add them together using the usual notion of function addition, do you get a real-valued function? Is it closed under addition? The answer is yes. What is more, f plus g plus h is f plus g plus h, and f plus g equals g plus f. The associative and commutative properties of addition hold. Is there a zero function? The zero function inputs some number and outputs 0 for all x. If you add this to another function, it just leaves it alone. You're adding 0 to all the outputs, which means you get the same output. The additive inverse is just -1 times the function, If you add the negative of a function to a function, you end up with the zero function. Also, if I take 1 times a function, I get that function. A times B times F is the same thing as A times B times F. And the distributive law, A times F plus G is AF plus AG, and then A plus B times F is AF plus BF. It satisfies all of the properties of a vector space. We get a function space, the set of functions defined on a closed interval, AB. C, AB, is the set of all continuous functions on the closed and bounded interval AB. If you add two continuous functions, do you get a continuous function? Yeah, that was a theorem in Calculus 1. If you multiply a continuous function by a constant, do you get a continuous function? Yeah. This is closed under both addition and scalar multiplication. And since these are functions, it will satisfy the other 8 properties as well. That means this is a vector space. It's sometimes denoted by C0, AB. Which begs the question, if there is a C0, what is C1, AB? This is the set of all one-time differentiable functions that have a continuous first derivative. We call them continuously differentiable functions. Notice that the set of C1 functions is a subset of the set of C0 functions. In fact, it is a proper subset. There are functions that are continuous, but not continuously differentiable. Similarly, the set of continuous functions is a proper subset of the set of arbitrary real-valued functions on some interval. You can see then that we have vector spaces inside of other vector spaces. This will bring up the important notion of subspace that we'll study in the next section. Another important vector space is the vector space P. The set of all polynomials. If you add two polynomials, do you get a polynomial? Sure. If you multiply a polynomial by a scalar, do you get a polynomial? Yes. It's closed under those two operations. It inherits all of the other vector space properties by being a subset of the set of functions. This is a vector space. There are some others. There's something called Pn. The set of all polynomials of degree n or less. We have to include the or less, because if you take a polynomial of degree 2 and then add it to exactly the negative, you get 0. And 0 is not a polynomial of degree 2. It's a polynomial of degree 0. The 0 polynomial has to be in this set. The 0 polynomial doesn't have degree n. It has degree 0. So you have to have the or less. As another example, how about just the set of complex numbers? We're assuming here that our field is a set of real numbers. If you add two complex numbers, do you get a complex number? Do complex numbers satisfy the associative law, the commutative law? Is there a 0? Sure. Do there exist additive inverses to complex numbers? Sure, just they're negatives. How about when you multiply a complex number by a real number? Do you get a complex number? Yes, it's closed under their operation of multiplication. If you multiply by 1, does it leave the complex number alone? And the answer is yes. Is there an associative law? Sure. Couple distributive laws? No problem. This will be a vector space. In our next example, we're going to let n be some fixed vector in Rn. And we're going to define V to be the set of all u in Rn such that n dot u is equal to 0. What do we mean by dot if n is the vector a1 through an, and if u is vector u1 through un, then n dot u is by definition a1 u1 plus a2 u2 through an un. Multiply the corresponding coordinates and add them up. This is the definition of the usual Euclidean dot product. Also note that in our usual understanding of Euclidean dot product, two vectors are orthogonal, meaning they have an angle between them of 90 degrees, if their dot product is equal to 0. We're defining V to be all of the vectors in Rn that are orthogonal to some fixed vector n. The set V inherits most of the properties of a vector space by being a subset of Rn. There are only two properties that are in question, and those are the closure laws. Do the closure laws hold for this particular set? To this, suppose U and V are elements of this proposed vector space. We know then that this implies n dot u is 0 and n dot v is 0. The question is, does n dot u plus v equal to 0? Let's calculate n dot u plus v. Well, the dot product does satisfy a distributive law. This gives us n dot u plus n dot v. And we already know that both of those are 0, and so we do get closure under addition. Now, is it closed under scalar multiplication? We'll take n dot a scalar times u. The usual dot product does have the property where you can associate the scalar a with either of the factors in the product or bring it out. But if n dot u is 0, we're having a times 0, which is 0. Therefore, we are in fact closed under scalar multiplication. We deduce then that this set V is a vector space. We've been using the term without a proper definition. A vector is an element of a vector space. So once you have the definition of vector space, any element of that will be a vector. So for example, 1, 2 is an element of R2, so 1, 2 is a vector. f of x equals x squared minus 1 is an element of P2, a set of polynomials of degree 2 or less, and we know that's a vector space, so x squared minus 1 is a vector. There are certain properties of vector spaces that you need to know and you need to know how to prove. Let V be a vector space. Our first property is that additive inverses are unique. Our definition of vector space did not say that there was only one zero vector. It left open the possibility that there could be several different zero vectors. However, we will prove that if you have a set that satisfies those 10 properties with 2 operations, then there can be one and only one additive inverse, one zero vector. Second, if you take 0 times some vector, you will in fact get that unique zero vector. Third, the -1 times a vector will give you the additive inverse in every case. 4, if you take a scalar and multiply it onto the zero vector, you get the zero vector. And 5, there's a certain zero product theorem. If C times V is the zero vector, then either C is the zero scalar or V is the zero vector. The zero product theorem, you'll recall, is if A at B equals 0, that implies A is 0 or B is 0. Something like that will be true for vector spaces, but it's either the scalar is the zero scalar or the vector factor is the zero vector. Property 1 is a classic uniqueness proof. Uniqueness proofs typically go something like this. If you want to prove there's only one of something, assume there are 2, then prove that they are in fact equal. So we're going to suppose 0, 1 and 0, 2 are zero vectors. What do you get when you add them together? You have to get 0, 2 because 0, 1 is a zero vector. But by the same argument, 0, 1 plus 0, 2 had better be 0, 1, since 0, 2 is a zero vector. Now, equality is always symmetric and transitive. The symmetric property of equality is that A equals B if and only if B equals A. The transitive property is that A equals B and B equals C implies A equals C. A equals A is called the reflexive property. Every equality relation satisfies these 3 properties. So this equal sign will in fact satisfy these 3 properties. What we get, therefore, is that since these are the same, is that 0, 1 equals 0, 2. So they're the same. On part 2, we're supposed to prove that 0 times a vector is the zero vector. Let's start on the left-hand side. But note that in the set of real numbers, 0 plus 0 is 0. By the distributive law for vector spaces, we can distribute and get 0 times v plus 0 times v. Now, By the existence of an additive inverse, we're going to have the following. Whatever this is, it has an additive inverse. And when we add that to each side of an equation, on the left side, we have to get the zero vector. It's a question of what we get on the right-hand side. By the associative property, we can reassociate the sum on the right-hand side. We'll have the negative of 0 times v plus 0 times v, and then plus 0 times v. This gives us 0 plus 0 times v, and if you add the zero vector to anything, you get that other thing. We finally conclude that 0 times v is the zero vector, and the proof is over. This is true for arbitrary vector spaces. Next, we need to show that negative 1 times v is the additive inverse of v. That's pretty easy. The proof goes like this. Let's take v plus negative 1 times v. By the property of 1, this is going to be 1 times v plus negative 1 times v. And then by the distributive law, we'll get 1 plus negative 1 times v, and that gives us 0 times v, which we now know to be the zero vector. That tells us then that negative 1 times v is the additive inverse of v. We next need to show that any scalar times the zero vector is the zero vector. To prove this, note that c times the zero vector is c times the zero vector plus itself. That's c times the zero vector plus c times the zero vector. We can now apply the additive inverse to whatever this is to both sides. On the left, we of course get 0. On the right, we can use the associative property to reassociate this as negative c times 0 plus c times 0 plus finally c times 0. When you add something to its additive inverse, you get 0, and when you add 0 to something, you get that other thing. We deduce then that c times 0 is 0. Finally, we need to show if c times v is the zero vector, then either c is the zero scalar or v is the zero vector. If c is 0, then we are done, because c is 0. If c is not 0, we need to prove that v is the zero vector. What we'll do is we'll take 1 over c times the quantity c times v. But by the associative property, we can write that as 1 over c times v. And 1 over c times c is 1. And 1 times a vector is a vector by the property of 1. On the left-hand side, we have 1 over c times what we're presuming is the zero vector. And we've already shown that if you rescale the zero vector by something, you get the zero vector. We deduce then that v is the zero vector, and that completes the proof. We're having you play with these operations abstractly so that you will deeply understand them. This is one of the reasons why Archimedes drew straight lines as arcs of circles, and he drew arcs of circles instead of straight lines. He wanted to force himself to think abstractly about the properties involved. Similarly, we want you to think about these properties and not be stuck to certain ideas that you've had about them in the past.